Hi. So in this new episode, we'll discuss sequential equilibrium, which is a extension for the notion of subgame perfect equilibrium to the extensive games with imperfect information. Okay, so we previously have studied the definition for the extensive form games with imperfect information, and we further restrict the games to only the games that has some perfect recall. Okay, so now we simply extend the SPE that we discussed previously to this new solution concept. Okay, and that will be useful for this kind of game with imperfect information in extensive form. Okay, so this sequential equilibrium was a from a paper by Krebs and Wilson in 1982. Okay, there were a lot of great works in game theory during that period, right? And later, if we have time, we could introduce some of the other papers later. Okay, so let's first take a note. So this sequential equilibrium will be sort of extension of subgame perfect equilibrium to the extensive games with imperfect information. Okay, and we know that there is another solution concept called perfect Bayesian equilibrium, right? So later we'll also introduce that and see the differences between that and this solution concept. Okay, so before we give the definition, let's first draw a game from the textbook from figure 220.1. So where we have this game, so player 1 moves first, could choose either L, M, or R, left, middle, or right. So if L, then game ends with 1-1 payoff, 2-2. If M or R, then player 2 gets to move, but player 2 has an information set here that player 2 cannot distinguish from those two actions. And what the player 2 could choose is to choose either L or R from player 2 or L or R here. Okay. Then the game ends with 3-1, 0-2. So here will be 0-2 and 1-1. Okay. So here, because we have this information set for player 2, so we cannot really adopt the subgame perfect equilibrium to analyze all those subgames, right? Because as long as we connect those dots, connect those nodes, those histories with the information sets, then this will become a whole game of a whole subgame, right? As a whole. So we need some other solution concept to help us to sort of cut or to analyze more specifically toward this information set, right? So, and recall that we have already used this concept called belief, right? So belief is something defined on some probability measure to measure this probability of some player think that this game is reaching some history, right? Or previously we used belief to induct Bayesian games, right? So those would be quite similar concepts. But in short, beliefs are nothing but just some distribution over a state, right? Or here, this belief would be a distribution over some histories, right? So all of those beliefs are just some probability distributions. Okay, good. So this is the game that we're going to analyze and to implement this solution concept to this game. Okay, so now let's forget about it for now and let's go to the definition of the solution concept. Okay, so before we define this sequential equilibrium, we need to define some of its elements. Okay, so we call this something as assessment. Okay, so an assessment in an extensive game is a tuple beta and mu. Okay, so this beta is a profile of behavioral strategies. Okay, behavioral strategies. Okay, so behavioral strategy is simply a randomized strategy on each information set, right? So, and that is the counterpart for the mixed strategy, right? So mixed strategy is a randomized strategy on the pure strategy profile, right? So those would be there are some minor difference, but here this is a definition based on the behavioral strategies. Okay, so profile behavior strategies, and mu is this belief function, right? So it's a function that assigns to each information set a probability measure on what? On the set of histories in this information set. Okay. So as we just mentioned, this mu is just a belief function, right? So that gives some probability on those different histories that could reach this information set. Okay. So that gives the chance or the probability that this player thinks that which history is played previously, right? And that's very straightforward. So, okay, so now we define this game. So we have all the tuple for this game. Okay, so let beta and mu be this assessment in this extensive game gamma, which is a tuple with player set, history, player function, and this is remember this is a prior belief from nature, and this is the information partition, and this is the preference relation, right? Okay. So this interpretation of mu, and we refer to as this belief system. Okay. So this is a belief system. All right, and so this belief system is we can interpret this as this follows. So mu, given some information set, and as we just defined, right? So in the some information set, so the probability of some history age is the thing that we want for the player, right? So that player pi, so is the probability that player pi, so for this information set, so the player assigns to the history, okay, in this information set, okay, and conditional on this I being reached. Okay, so here immediately we could see that we'll need Bayes rule to update the beliefs, right? So because we have those all those possibilities of those histories coming into this information set, so given that this information set is reached, so we want to know that what is the probability of we're really having some specific history, right? So the belief of that. So that has to be just a easy, straightforward implementation of Bayes rule, right? Okay, so good. So that's the belief system, right? And we also want to have some definition for this sequential rationality. Okay, so an assessment is called sequential rational. Okay, sequential rational, or sequentially rational, right? If for each player I and information set, the strategy of player I is a best response, as we did in Nash equilibrium, right? So that has to be best response to the other player's strategy. Okay, and we need to define that on some outcomes, right? Okay, so to do that, okay, we need something else. So player strategy, and of course, given I's belief at I, okay? So here we shouldn't forget about those beliefs, right? Because here we always have some sort of imperfect information in this game. Okay, so to use the outcome to define this this concept, so we need to first define this outcome. So outcome O, okay, so which is function of this beta and mu, and given some information set I. So this outcome of beta and mu, this assessment, conditional on this I. Let's define that to be the distribution over the terminal histories, right? We always define the outcomes over the terminal histories. And those histories has to be determined by beta and mu. And it has to be conditional on this information set being reached. Okay. Okay, so in math, let's write down some notations for this definition. So let's let this H star history be a sequence from A1 up to AK. Okay, so that has to be a terminal. Let's define that to be a terminal history. Okay, and we also let this H from A1 up to AL. This is in this information set I. Okay, and this L is less than K. Okay, so we need some requirements for this outcome such that this O, beta mu given is I, if that takes H star, okay, and that is 0, if there is no subhistory of H star in I, right? So it means that the information that game has reached I, it has to be ruling out this H star, okay? And second, O of beta mu given I, if we take H star, that is mu I H. Okay, and then multiply all those probabilities, right? From K is L up to K minus 1, and multiply all those betas. Okay, player A1 up to AK, and here A1 up to AK, and AK plus 1, okay? Good. So this is a very technical definition for the outcome, right? But as long as we know that this is defined on the terminal history, then we don't need to bother to further expand that. Okay. Good. So all right. So now let's start to define what we mean by the sequential rational, right? So that would be a very important concept compared to this, right? So let's do that. So we have this game with extensive form and imperfect information, H, P, FC, graphic I, and preference relation. Okay, so it needs to be an extensive game with perfect recall. It could have some imperfect information, but it has to be something with perfect recall, right? So the assessment beta mu, okay, so we know this assessment. So it is called sequentially rational. Okay, if for each player I and information set I, we have the following. So we compare those in the on the outcomes, right? And as we did in Nash equilibrium. So this outcome of beta mu given I, so this is weakly preferred to the other one with beta minus I and beta I prime. Okay, so this means that if player I deviates, right, to something else, and say mu for every strategy beta I of player I. Okay, so this definition is very straightforward, right? So if this player I plays this such strategy, behavior strategy compared to all the others, and this gives the weekly the highest payoff, or it is weekly preferred than all the others. Then we say that this assessment is sequentially rational, right? And given this belief. Okay, so good. So this is the definition for sequentially rational, and we define something else which is called consistency, and that will be also useful in the definition for this sequential equilibrium. Okay, so now we define the other part, which is called consistency. Okay, so again, we don't need to bother to write this game gamma again. So we know the gamma. Okay, it has the same parts as before. So an assessment beta mu, we say it is consistent if, so we're going to use the limits of a sequence to define this consistency, okay, because when you define this behavior strategy profile to be completely mixed, if it assigns positive probability to every action at every information set, okay, and here intuitively why do we need this consistency for this system concept is simply because of the base rule, right? So if we have 0 on the denominator of the base rule, then it doesn't work. So we need to give at least some number, which is maybe just slightly bigger than 0, and that will work, right? Okay, so if there is a sequence, okay, so we use some sequence with limits, And it's the same if we analyze any specific games, right? We simply give some very small numbers, such some epsilon, which is just bigger than 0, and give that to some something that was originally 0, right? And that would be helpful for us to implement this solution concept. Okay, so this will be sequence from n is 1 up to infinity. Okay, so those many of assessments that need to converge to this assessment beta mu. Okay, and it's in the convergence in the Euclidean space. Euclidean space. Okay, and it has some property. Okay, so what is the property such that for each strategy profile, okay, beta n is completely mixed, as we just mentioned. Okay, so we don't have 0 anymore, and that'll be useful. That'll be available for the base rule to apply, right? And that each belief system mu n is updated or derived from beta n using the base rule. Okay, good. All right, so the fundamental idea behind those requirements is that the probability of the events conditional on 0 probability events must approximate the probabilities that are derived from the strategy that assign positive probability to every action, right? So then we simply give some very little probability to those 0 probability events, okay, to be able to use the base rule. Okay, so although it looks very unnatural, but it really helps us to implement the base rule and use this belief system to be able to analyze the games, right? Okay, good. So we are ready to formally define the sequential equilibrium. Okay. So we say that, okay, so this is the definition for a sequential equilibrium. Okay, so an assessment, let's call this SE, that's too long. So assessment is a sequential equilibrium of a finite extensive game with perfect recall if it is sequentially rational and consistent. Okay. Okay, and this definition is very, very simple because we have already defined the parts of those things. Okay. And we could show that every finite extensive game with perfect recall has a sequential equilibrium. Okay, but we don't need to bother to do that, and we could always refer to the textbook for this proof in a proposition later in this chapter. Okay, so and that should be just a proof of the existence. Okay, as we did a lot of times before. Okay, so And it is also clear that if this assessment beta mu, it is a sequential equilibrium, then this beta, it has to be a Nash equilibrium, right? And that's very straightforward. So, and further, in an extensive game with perfect information, beta mu is a sequential equilibrium if and only if this beta, it is a subgame perfect equilibrium. Okay, so those would be the important relationships, or this is actually is called refinements, right, between those different solution concepts. Okay, so we don't need to bother to write that down, but we'll just have some intuition for that. Maybe later, after we finish the series, then we could have a table to summarize all those different solution concepts. Okay, so now let's go back to the example that we had in the beginning of this episode. So let's find that. Good. So this will be the game that we're going to analyze now. Okay, good. So, all right. Now let's have a look on this solution concept. Okay. Good. So, what is the assessment for this game? Okay. So the assessment beta mu, okay, so it's where it's for player 1, beta 1, to player L, it has probability of 1, okay. And for player 2, playing R, it has a probability of 1. So it means the probability of player 1 playing M or R will be 0. And the probability of player 2 playing L will be 0 as well. And more importantly, it's not finished yet. We have this belief system, right? And mu, if the information set is MR, right? So for player 2, which is this information set, then let's say the belief of this history was from M. Let's give a number to that, okay, alpha, which is just some number between 0 and 1 for any alpha, okay? So this assessment with those requirements is, it is first, let's verify it is consistent, okay? So how do we do that? We simply use the limits, right? So since those are, since it is the limit, let's take some small number, okay, which goes to 0 of those assessments in sequence, okay, where let's say this beta 1 in the sequence will be, let's simply minus this small probability from the probability of 1 and give this small probability if there were 0 originally, right? Okay, and here we have this alpha, right? So we have already defined this as the belief. So and 1 minus alpha here, okay. All right, and for player 2 in sequence, so their behavior strategy would be, let's give this strong probability to 0 and use 1 to minus that for the other, right? Okay, so let's use some colors to correspond those. So this corresponds to that, right? And this, in limit, it should converge to this, right? Okay, and that will be very straightforward. Okay, good. So, oh, and something else, right? So we forget the mu. So mu also has to be converging in the sequence. So mu in this sequence would be, okay, where's this? Okay, for this information set MR, let's say the probability or the distribution of this information set coming from M history is alpha, okay? All right, and that goes to here, right? Right, because we already have the numbers, so we don't need any to add that for any small probabilities, okay? Good. And that is for every small positive number, okay? Good, so that completes the only one part, right? So for the other part is the sequential rationality, right? So let's say that for alpha that is greater than or equal to the half, this assessment beta mu is also sequentially rational. Okay. So together with the sequentially rational and consistency, then we have this solution concept as the sequential equilibrium, right? Okay, so why is that? We were saying that if alpha is greater than a half, then this assessment is also sequentially rational. So we could see this simply from the game tree, right? So if alpha is not less than a half, then what is this alpha here? So this alpha would be the probability of playing M, right? So we write a little alpha here, and this would be 1 minus alpha, right? So if, let's say, we have said that if alpha is greater than or equal to a half, so it means that this M is more likely to be played, right? So in this case, if player 2 thinks that M was played previously, then the player 2 should simply choose R, right, to get this utility of 2, right? So, and that would be consistent with the behavior strategy of player 2, that if this information set is reached with this belief, then player 2 chooses the probability of 1 to play R, right, rather than instead of playing L, okay, because playing R gives a high utility of 2. Okay, good. And here, so upon observing that, then player 1 could see that if R is also played by player 2, then player 1 could get 0, right? So, and player 1 would simply choose this L here, right? So player 1 won't bother to reach any of those in M or R, right? Okay, good. So that is a very good example in the new solution concept called sequential equilibrium for the extensive form game with some imperfect information. That is allowed, but here we do not allow for any imperfect recall. Okay, good. So later we'll show some more interesting examples and the related solution concept called perfect Bayesian equilibrium and compare that to this. Okay, good.